Hello everyone, welcome to my YouTube channel. Today I will teach about the transition metal alkene complexes. So alkene complexes are extremely important because they are the first step of alkene functionalization. So like here the alkene moiety is bound to the metal center, and here the metal hydride was inserted to the alkene moiety to form this alkene moiety, and further reaction occur. So virtually all transition metal complex from olefin complexes or reaction with the olefins. So olefin ligands are extremely soft. The ancillary ligands should be soft alloys as well. So example of some alkene ligand is here the rhodium ethylene moiety is bound. Here the nickel COD whole 2 cyclooctadiene complex. Here iron 1,3 butadiene complex. So first we should know about the structure of olefin complexes. So here alkene is a pi donor and pi acceptor ligand. So it donates the pi electron density to the metal center and also accept the electron from the metal center. So here the pi electron density is donating to the vacant d orbital of the metal center. It is the field pi electron. So the empty metal hybrid orbital. So this donation occur, and another this in this example the electron from field d orbital is donated to the empty orbital of the empty pi star orbital of the alkene. So that this has the metal field orbital to alkene back donation is occurred. So the pi acid ligands donate electron density into the metal d orbital from the pi symmetry bonding orbital between the carbon atoms, and the metal donates electron bank from it field d orbital into the empty pi star antibonding orbital of the ligand, similar to the dihydrogen sigma complex. So both of these effects tend to reduce the CC bond order, leading to an elongated CC distance and lowering its vibrational frequency. So that means, so when the pi electron density donated to the metal center, it lowered down the CC bond order. So more the electron donating to the metal center, more the CC bond order will decrease. So next we should know the coordination model of the metal olefin complexes. So metal olefin complex can bound to two-way. One is L time mode and another is X2 time mode. So in both cases, ligand is considered as a two electron donor in covalent method. So in X2 and L, in both cases, the ligand is considered as a two electron donor. But in ionic model, X2 configuration has two electron charge, two negative charge, and considered as a four electron donor. And in the ionic model, the L configuration does not change the oxidation state of the metal, still considered as a two electron donor. So one can consider L as an intermediate structure in the oxidation addition to the alkene ligand to form X2. In the X2 form, C atom of the alkene rehybridized close to sp3. Apart from the crystallography studies, the 1H and 13C NMR spectroscopy are useful to determine the which nature of the metal alkene bond. So that means here the metal alkene is bound in two way. One is the L type, another is the X type. So in the L type mode, both in ionic and covalent method, the alkene ligand donate 2 electrons to the metal center. But in the X2 type mode, the alkene ligand donate 2 electrons in covalent method, and in ionic method it donate total 4 electrons to the metal center. So here the factors favoring the X2 type binding, that means the stronger donor ligand in the metal center, that will favor the X2 type binding. The net negative charge on the metal complex will favor the X2 type binding, and the low oxidation state on the metal center also favor the X2 type binding mode of the alkene complex. So the reactivity difference between these two bonding types are: in the L type ligand, alkene is electron deficient, is prone to attack by the nucleophiles, and in X2 type bonding mode, the carbons are electron carbanion like, prone to attack by the electrophiles. So olefin bind strength is very sensitive to the steric changes. So binding strength is depend on the steric property. So ethylene bind to the metal center more tightly compared to the propylene, compared to the cis-butene, compared to the trans-butene. So its binding strength is depend on the steric property of this alkene ligand. So chelating dienes are more stable complex from the simple alkenes due to the chelate effect. So in the metal alkene complex, it is generally observed that the more stable complex is always formed in the cis alkene due to the steric factor in case of complex where the cis-tern isomerism is possible. And the another point is the presence of electron withdrawing groups on alkene increase the strength of the metal and alkene bonding, while in electron donating group decrease the stability. And chelating dienes such as cyclobutadiene, non-boradine show the stabilization resulting from the chelate effect. However, it may be noted that this can be displaced from the metal by stronger coordination ligands such as phosphine. And complex with the cycloalkenes, which have the strain rings, display increased stability. The ring strain increase the energy of the cyclohexane ring compound, making it the beta donor to the metal center. And the changes the in hybridization of bonding release the strain in alkene. For example, non-boron binds too strongly to the metal compared to the cyclooctadiene. So to summarize, the same factor that lead to lowering the mu CO frequency in infrared spectra of the metal carbonyls also lead to the greater cyclopropane character in the alkene complex. For example, strong donor CO ligands on the metal like the CO ligand, the net negative charge on the metal complex, and the particularly low oxidation state of the metal will lower the this CC bond stretching frequency. This means the lower oxide palladium to copper 1 Ag1 alkene complex favor the L-type mode of bonding, while those are nickel 0, PD 0, platinum 0 complex tend to favor the X2 type bonding mode. In addition, the presence of electron withdrawing substitute on alkenes, electron withdrawing substitute on alkene also favor this X2 type bonding mode. So the most well-known example of this metal olefin complex is the Jesus salt, which was discovered in 1827 by reacting the PTCl whole 2 minus and ethanol. But however, its structure was only determined about 150 years later. One of the unique feature of this complex is that the ethylene molecule occupies the fourth coordination site of the square planar complex with the CC axis perpendicular to the platinum ligand plate. So here the upon coordination to the platinum, the CC bond length of the non-coordinate within is 134. Upon coordination to the metal center, it bond length is increased. So some basic basic features of the which is palladium Cl3 ethylene molecule is the PTCl3 moiety forms a nearly planar group with the PT atom. That means the 3 chloride atom chloride ligand is more or less in the planar position with this PT platinum. The platinum Cl bond turns to the ethylene group. It's significantly longer than the platinum cis-platinum Cl bonds. The C atoms are approximately equidistant from the platinum atom. That means the 2 C atom of this ethylene moiety is equal distance to from the platinum atom. The distance from the midpoint of the CC bond to the platinum atom is 2.022 Armstrong, and the CC distance is 1.375 Armstrong, which is slightly longer value than the found in the free ethylene, that is the 1.337 Armstrong. So indicating that some d pi p pi star back bonding from the platinum to atom to ethylene molecule. That means upon back bonding from platinum to ethylene, it's increase the bond order of the CC bond length. So that's why the CC bond length is increased, and back bonding is also indicated by bending of the 4 hydrogen atom away from the platinum atom. So both the magnitude of CH bending and CC bond lengthening are considerably smaller in Jesus salt than the metal complex with C2F4 or C2CN4, suggesting that the amount of the metal ligand back bonding may greater in the complex than in those involving with ethylene. That means the electron donating withdrawing substitution on the ethylene moiety like fluorine or cyano that will favor more back donation to the metal center, and that will increase the CC bond length, and the magnitude of the CH bending is more compared to the ethylene. So when PTCl3 moiety is replaced by the much more pi basic PTPPH3, a greater back donation is observed, that will increase the CC bending as longer the CC bond length. So this is an example. So here the PTCl3 ethylene, the CC bond length in 1.375, and for the when the Cl is replaced by triphenylene phosphine, the CC bond length is 1.430. So that means in this PPH3CH4, the phosphine group is a more sigma donating ligand, so that will increase more electron density onto the metal center, that will favor more back donation to metal to the ethylene moiety. So that's why the CC bond length is increases. So now I will discuss about the synthesis of metal alkene complexes. So metal alkene complexes can be synthesized in various methods. So first one is the substitution reaction. That means here first the PTCl4 is the one ligand is substituted by the ethylene moiety from this metal alkene bond. So here the substitution of the halo ligand is promoted by the chloride scavenger that either produce a non-coordinating anion or form an insoluble salt halide. So in the substitution reaction, one halide ligand is replaced by the ethylene. So this reaction with favor if in the reaction medium some chloride scavenger like AlCl3 is added. So that will favor the or of the formation of the metal alkene bond. So like that, rhenium Clco5 that react with the ethylene in presence of AlCl3. So that will form the rhenium C2H4 and CO5 complex and AlCl4 minus anion. And if another example is the iron iodide CpCO2 and in react with the C2H4 and AgBF4 that will form the iron alkene complex and AgI will precipitate. So thermal basis metal alkene complex can be prepared by the thermal ligand substitution reaction. So here FeCO5 plus react with 1,3-butadiene in 135 degrees centigrade temperature at core 20 bar. That will form the FeCO3 and 1,4-butadiene is coordinate to the metal center and 2 carbon is detached from the iron. And another substitution reaction is a photochemical ligand substitution. So here the manganese Cp star CO3 will ligand will react with this alkene moiety in presence of light that will form the manganese alkene complex. So next is the addition reaction. So addition reaction means the coordinately unsaturated complex can add olefin ligand without replacement of another group addition. So that means a unsaturated electronically unsaturated ligand moiety complex that will react with this alkene moiety to form this alkene metal alkene bond. So that here the iridium Cl chloride CO PPH3 whole 2, it is a 16 electron complex. That means it is a coordinately unsaturated react with this alkene moiety to form this metal alkene complex, which is a 18 electron complex. So by coordinate to the alkene moiety, it's a 18 electron, so it gives stability to this metal complex. So simple method for the separation of the isomeric olefin by recrystallization of the silver nitrate redox is based on the following of equilibrium. So here AgNO3 reacts with the 2 olefin in presence of ethanol. So here Ag olefin whole 2 and NO3 is precipitate. That's why the metal alkene complex is formed. So next is the metal reacting with the metal salt with the olefin and the strong reducing agent. So here the example is the nickel chloride. Here the nickel is plus 2 state. The Al-R3, what is the reducing agent with react with this 1,3-butadiene to form this intermediate nickel intermediate, and that reacts with this ethylene to form this nickel C2H4 whole 3. So here the nickel oxidation state is 0. So Al-R3 acts as a reducing agent. So next is the metal salt per olefin with a weak reducing agent. So here rhodium Cl3 and C2H4 in presence of ethanolic water mixture to form this rhodium dimer. So here rhodium is a +3 oxidation state. Here it is a +2 oxidation state. Here the ethanol acts as a reducing agent. So next is the metal atom ligand vapor condensation or the metal vapor synthesis. The metal atoms vapor are condensed with the gaseous ligand or into the ligand solution of a low vapor pressure on a cool surface. Upon warming to the room temperature, a metal complex are formed in the combination with the metal aggregation. So here the gaseous metal atom vapor, the iron vapor react to is this on octadiene cyclooctadiene react with this FeCOD whole 2. So next one is the nucleophilic attack onto encyl complex. So such nucleophilic addition are strongly, so here this APCO whole 3, this moiety is attack here Cl minus the nicobate, this attack with this attack here, and that will from the metal alkene complex. So such nucleophilic acids are generally regio stereoselective and takes place in the exo orientation. So next one, the beta hydrogen abstraction from the alkyl complex. So here this ApCO whole 2 Cp star and this alkyl complex, uh, it will form the metal alkene complex by the beta hydrogen abstraction to form these metal alkene complexes. So next we will consider the reactivity of the olefin complexes. So olefin complexes can do the substitution reaction and the nucleophilic attack onto the olefin. In the substitution reaction, alkyl complex can be used as a labile precursor because the moderated olefins are readily substituted by the dienes or the strong pi acceptor ligand. So like here the rhodium, as this ligand is, so here this monodentate alkene is substituted by various strong pi acceptor ligand or the chelate ligand like 1,3-butadiene or 1,5-cot. So that will form the corresponding metal complexes. So next is the nucleophilic attack onto the olefin. There is a concept of amplam. So here a very interesting outcome of bonding of an alkene to the metal is reflected in the reactivity of the coal. So the outcome of the bonding of an alkene to the metal is reflected in the reactivity of the coordinated alkene. Many simple alkene is the free state are so free state are easily subjected to nucleophilic attack, but don't undergo nucleophilic attack. So that means when alkene is in the free state, that will not bind to the metal, that will encourage the electrophilic attack on the carbon center, but not the nucleophilic attack. However, because of the deflected electron density on the alkene bound to the metal are prone to nucleophilic attack rather than the electrophilic attack. So that means upon the donation of the electron density to the metal, this metal alkene, the carbon atom of the metal alkyl complex is electron deficient, so that will prone to attack the nucleophilic attack. So the effect of the binding plays here an important role, the deciding of the reactivity of the alkene, and the inversion of the chemical character of alkene is called the amplan. So here are some example of this metal nucleophilic attack on the metal alkyl complex. Here the CH2COO Me2O2 is a nucleophilic. Here is attack to the this metal alkene complex to form this intermediate, and here the PPS3 as any act as a nucleophilic that will attack to the carbon atom to form this product, and here E2 this secondary amine, it acts as a nucleophilic, then lone pair of nitrogen will attack to this center to form this product. So the organic chemistry of benzene is dominated by the electrophilic substitution, but as a covalent ligand, it undergo nucleophilic substitution. So metal fragment with good pi accepting ligand or positive charge will be good candidate for activating an unsaturated hydrocarbon toward the nucleophilic attack. So of course, not all the unsaturated hydrocarbons are equally reactive, while the ethylene and benzene are quite reactive, and cyclopentadiene is one of the least reactive toward the nucleophilic attack when it is called into the metal center. So this is the reactivity order of this metal alkene complexes. So here the ethylene moiety is the most reactive compared to the all other metal alkene complexes, and the cyclopentadiene is the least reactive compared to the all other
metal alkene complex. The reason why the coordination activate the alkene for the nucleophilic substitution can be understood from the fact that the alkene moiety is not readily bound to the metal but oscillate around the equilibrium position. So if an ethylene ligand shifts sidewise as soon CC bond become polarized, so in an extreme case, the carbon atom is at one end could be thought to assume the cationic character, who is enchants the susceptibility towards the nucleophilic attack. The attack can be from a nucleophilic that is already bound to the metal or from the outside. For example, so in a Walker process, the alkene bound to the PD palladium unit undergo nucleophilic attack by a water molecule to form from outside. So another famous example is the Walker process or the nucleophile. Here, the water acts as a nucleophile. So here, the ethylene moiety is converted to the corresponding aldehyde in the presence of palladium Cl2 by nucleophilic attack of water and from palladium 0 and HCl. So here, ethylene is converted to the acetaldehyde in the presence of tetrachloro-palladium and water. So this is the valence sequence. So here ethylene react with the PDCl4 2 minus in presence of water to from this acetaldehyde and 2 in HCl form, and palladium is reduced to palladium 0. So this is the catalytic cycle of the Walker process. So first the PDCl4 2 minus, that so it react with the ethylene from this metal alkene bond. Then and water is did the ligand substitution reaction. One chloride atom is substituted by the water molecule to form this water about palladium intermediate. Next, another molecule of water is do the nucleophilic attack onto the carbon atom of the ethylene to form this alkylated palladium intermediate. Then another molecule of the chloride is detached from the metal center, and here the beta hydride elimination occur to form this metal alkene intermediate. So that will isomerize to form this intermediate. So next, via this intermediate, the acetaldehyde and the HCl is eliminated out to form this palladium 0. Again, this palladium 0 is oxidized in presence of copper chloride to form this C2Cl2 to form this our active in catalytic intermediate. So this is the catalytic cycle of the Walker oxidation process. So now I will discuss some problem on the metal alkene complexes. So first example is the arrange the following compound on the increasing order of ethylene CC bond length. So here the CC bond length will depend on the two factor. One is the electron density on the metal and the back donation to the metal to the alkene. So among these four complexes, the complex B is the iron is a +2 oxidation state and all other in the +1 oxidation state. So among the four metal complex, so B has least electron density onto the metal center. So that means the here the CC metal to alkene back donation is not favored. So here the CC bondage is shortest CC bondage for this complex B. So next, all the complex are in the +1 oxidation state. So now we should consider the metal electron density. Uh, so in complex A, B, A, C, and D, complex A has two CO ligands, complex C has one CO, one ET3 pre-ligand, and complex D has two ET3 pre-ligand. So here the deciding factor is the electron density on the metal center via the donation of the electron to a CO or the PT3 ligand. So among this CO and ET3 pre-ligand, so CET3 pre diethyl phosphine is more electron donating ligand compared to the carbonyl. So that means CO is a electron sigma donor, also pi acceptor, but the phosphine is a pure sigma donating ligand. So the phosphine will donate more electron density to the metal center compared to the CO. So that means the number of phosphine ligand will increase, the electron density will increase the electron density on the metal center. So that will favor the metal alkene back donation. So that will decrease the that will increase the CC bond order, and that's why the CC bond length will increase. So among these A, B, and C, D, the A has only two CO, so that and C has one triphenyl diethyl phosphine. So C has more electron density and D has more. So back donating nature is A, C, D. Back donation increases. So from A to D, the back donation increases. So that's why the metal CC bond length will increase. So final order is B, A, C, and D. So D has longest CC bond length. Increase order. Order of CC bond length. So my next question is the alkene complex P iron P trimethyl phosphate and eta 2 propene at the low temperature shows 4 peak and it's 13 on P NMR spectrum. Draw the structure of the complex, and when the same sample is one, the 4 peaks of the 13 P NMR spectrum collapsed into 2 peaks with equal intensity. Explain this phenomenon. So the structure of the complex, the Fe so this is the structure of this complex. Here 4 phosphine ligand is bound and the propene is bound in an eta 2 fashion. So when at the low temperature the first propene is bound, all the phosphine, all the 4, it is the octahedral geometry, all the 4 phosphine ligand trimethyl phosphine at the different chemical shift due to the unsymmetry of the alkene. So that's mean at the lower temperature this alkene is the bound to the interfacent is unsymmetric, so the all the phosphine are not equal. So all at low temperature, all the phosphine has so total 4 peaks correspond to the 4 different type of phosphine ligand. But when it is on the heating, the alkene is start rotating. That means this alkene is rotate, and that around the metal alkene axis, and that's time on the heating, the 4 phosphine are mm, now appear to the alkene as a two sets on the equatorial and the axial. So that means when it is when the complex is warmed, this alkene is rotated. So that time the two type phosphine on one is this equatorial and another on the axis. So that means upon hitting the complex, the two sets of phosphine, one the equatorial and one is the axial. So that time total 2 peaks are observed in 31P in a month. That's why the only 2 peaks are observed. Which of the next question is, which of the following metal alkene complex do you think look most like a metallocyclopropane? Depending answer. So metallocyclopropane means the alkene in bound to the metal center by a X2 type mode. So that means this is the metallocyclopropane structure. That means the more electron donation electron density will favor this X2 type ligand. So between these two complex A and B, so here both the metal in zero oxidation state, and one case the ligand is the PPH3 whole 2 and another case is CO whole 4. So that means between this PPH3 and CO whole 4, CO is a pi sigma donating and pi ligand, and phosphine is a pure sigma donating ligand. So that means the electron donating property of the phosphine is better compared to the alkene compared to the carbonyl. So the phosphine bound metal complex which has more electron density to the metal center, so that will favor the more back donation to the metal to ethylene molecule. So here the complex A will favor the metallocycle propane structure compared to the complex B. So thank you.